Hello and welcome everyone to the latest Green Tech Media webinar. This webinar is sponsored by Tigo Energy and my name is MJ Shao. I am a senior analyst with GTM Research. Before we begin, just a few quick housekeeping notes. We do have a fancy dashboard here where you can download the slides, you can share the webinar, you can learn a little bit more about GTM Research and about our speaker today. And most importantly, you'll see that you have a little Q&A box. So at any time that you have a question, feel free to type your question into that question and answer box. We'll have a little bit of time at the end of this webinar to go through those questions and try to answer as many as we can. But if we can't get through them all, we'll also try to answer some afterwards as well. So this webinar is entitled Quantifying the Impact of Module-Level Power Electronics, and again is sponsored by Tigo Energy. And today from Tigo, we will have Paul Grana, who is the Director of Marketing. Now before I let Paul take it away, I just want to give some brief background and context on the module-level power electronics market as GTM Research sees it. And one of the things to point out is that module-level optimization, module-level power electronics is not a fad. And what we've seen, especially in the U.S., in California, is a large pickup of microinverters and DC optimizers being installed in the field. So that the market share of module-level power electronics has risen in the past 6 quarters from less than 6% of the total market, and this is residential commercial market, to 12%. Now, this space is very, very crowded, and there's a lot of, and beyond the early movers like Enphase Energy and SolarEdge and Tigo Energy, we have seen a lot of different companies, different types of companies come in and try to approach the distributed optimization market. Everything from inverter vendors building out their product suites to component suppliers, people providing the IC chips and looking to just provide to the standalone module optimizer providers. So, and all these companies have different routes, how they're getting different financing, and also different approaches to market, whether that's through a standalone product that directly to installers and developers, or whether that's more of an OEM model where they're providing it to the module manufacturers, or it's part of a larger system. Now, what's going to unlock this market even more pickup that we've seen already is addressing the historic industry concerns about the market. So things like cost, the risk, the complexity, and the reliability, looking at things from a total system perspective instead of just at a product-specific level. So for example, when we're talking about something like reliability, instead of looking at it, what is the individual reliability of this module-level optimization unit, thinking about it in terms of what is the total system availability, because now I have, when I lose, for example, one optimizer, I'm only losing one module instead of a string inverter or a central inverter. So how does that then unlock the market? And just to step through one brief example of that, looking beyond just the historic value proposition of module-level optimization, if we remember back when module-level optimization first came into the market, it was all this talk about performance, shaded performance, and how that's going to drive up your kilowatt hour and the kilowatt hours and drive down your levelized cost of electricity. But if we look beyond that and look how we can even create net upfront cost savings through installing module-level optimization, we can start to see that there is a shift in the value proposition of this part of the industry. So in this example, if we look at, let's start with a commercial system that's using DC module-level optimization. And we start with our base inverter around 26, 27 cents a watt in terms of upfront costs. and then we add a premium in terms of our DC optimizer, so something like 14 and 15 cents a watt, and suddenly we're at 40 to 41 cents a watt. Now before the evaluation of whether this is worth it or not would have been, am I going to get the extra performance out of that 14 to 15 cents a watt to justify paying that extra cost? And the answer is, unfortunately, unless there's some major shading in the system, probably not. But if we take a look at the whole system and look at it from a total system cost perspective. So now, because we're using DC optimizers, we have a fixed voltage input to the inverter, and we don't need things like the MPPT. We can do things like stretching the strings by 30% because, again, we're fixing the voltage output from these strings. And then we can also increase the nameplate capacity of the inverter, because we have this voltage control ability, and we're running the inverter basically hot more of the time. And I believe Paul will go into a little bit more about how Tigo Energy approaches this. But if we take all those savings and then we look at the total net cost of the system, suddenly we're under what just the base central inverter would be. Now, of course, this is all theoretical because it's going to take a sophisticated developer. It's going to take an integrator who has experience to really be able to take advantage of these costs. But it is one of the things that we believe will drive the module-level power optimization market forward. And so I'd like to now pass it over to Paul, who can talk about how you can start to you can actually quantify the return on investment through using module-level electronics, through new modeling systems, and looking at, again, this total system perspective instead of just looking at the performance benefit of module-level power electronics. So once again, Paul Grana, who is the Director of Marketing from Tigo Energy. Go ahead.
Thanks very much, MJ. So thanks, everyone, for joining the call. As MJ said, these products are increasingly being adopted across global markets, not just North America and not just California. Of course, Tigo, being a market leader, as you can see here, one of our examples on the East Coast, this is a 2.2 megawatt system that went into Vermont just a couple weeks ago. Now, as we are expanding our presence in the market, we are definitely moving down a trajectory of gaining a better understanding of the drivers of the value. A couple of years ago, most people knew there was something there, but had to use judgment. And increasingly, we've got more and more systems that can both tell us what the hardware benefits are in terms of having longer strings, what the performance benefits are in terms of mitigating mismatch, and what the overall lifetime benefits are in terms of having better data to spot failures and tell exactly what they are. Now, a quick background on Tigo. We are the market leader in DC power electronics. We make a small PCB that goes into the junction box of a smart module. That's what you can see here in this picture with that small PCB behind the module. We've hit a number of recent milestones, including receiving a positive third-party validation with the technology review from BEW. We're on a number of large systems, not the least of which is that 2.2 megawatt that we just saw the picture of. And we've recently received our TUV certification for North America and Europe so that we can ship these fully integrated smart modules. So there's been a lot of talk of smart modules, and to our view, the mark of a smart module is having the electronics right inside the junction box. That's really the only fully elegant solution to bring a product to market. Tigo Energy is excited to be the first company that brings that to market. Part of why we're the partner of choice is that we are fully inverter agnostic. So when you work with Tigo Energy, we can work with any inverter that's on the market. So that's an important distinction between this architecture and a different one that includes microinverters or that includes a fully integrated inverter. Now, as we're expanding into the market, there's a lot of commercial traction. So these products work in residential, but they're particularly good in commercial because the cost scales very, very well. And as we're working with these commercial customers, we are working on a lot of very good modeling for how to help them understand what the drivers of the ROI of these products are. So what we'll be talking about today is starts with energy harvest, but goes much beyond that. As MJ said, there's an aspect of expanding a system size. There's an aspect of reducing the electrical costs, and then also reducing the O&M and costs and improving uptime. Now, a brief administrative note before we get started. First of all, our data does belong to our customers. So both our existing customers and our future customers can rest assured we don't use these as chances to show specific system installations. We have no desire to be the AC Nielsen of solar, but we do use the data in aggregate in cases where it can help make the industry better off. In terms of analysis, some of what you'll see here is actually done with a third-party tool, which we can use to tell what the energy impact is of module-level electronics. You can consider it similar to very much like a PV syst model, but at the module level. So a lot of the analysis is powered by that. And then finally, on a number of the slides, we do have a lot more data, and I'll just be presenting the summaries. If you see this green icon on the bottom, feel free to follow up with one of us after the show. There'll be a number of email addresses, but primarily it's sales@tigoenergy.com, and we can send you the data or reports or templates that are behind a lot of the stuff that I'll be presenting here. So getting into the detail, first of all, really understanding and quantifying the drivers of mismatch. Much more than shaded systems, we are finding sources of mismatch in completely unshaded commercial scale systems. Now, one of the first sources is mismatch from clouds. Now, it's very difficult to understand what the magnitude of that is because, of course, any single weather station is only going to be measuring one point at a time. We, however, were pretty lucky to get some data from NREL that they released just a few months ago. So some in the audience may be familiar with the NREL Oahu data set. They collected information from 17 light meters in one location in Oahu. So this went from March of 2010 through March of 2011. And not to mention that, they also collected the data at 1-second intervals. So this gives us a really nice way to look at the amount of mismatch driven by the clouds there. Because again, as clouds move over one portion of the array, you may have some of the array clouded and some of the array getting full sun. What we found was actually pretty surprising. We found a total average standard deviation of 15.4%. That's averaged throughout the year, weighted by the amount of power that was being generated at that time, or I should say weighted by the average irradiance at that time. So that would drive approximately 5 to 8% in lost energy due to mismatch. That value actually went up in the summertime, as you can see here in the chart at the bottom, and it also was highest at the middle part of the day, even as a percentage. So that was a pretty tall number. Now, granted, that's in Hawaii where there are a lot of high-altitude clouds, but at least we're starting to get a good legitimate data set for how much mismatch there is in unshaded arrays. Additionally, we can take the same type of view at our own fleet. What you're looking at here is a histogram of how many module hours are close to the peak module. So if you're at or near the peak, that shows up in the 0 bar here. And what you see is on our fleet, which spans both residential and commercial, we have an average standard deviation of 11.3%. So this is somewhat in line with the NREL. It's actually a bit lower than what we saw from the Oahu data. So again, sort of the ambient cloud-based mismatch is real, and we see that both in Tigo's data set and in third-party data sets. So that drives some of the difference in irradiance that modules will see across an array. Additionally, modules tend to run different temperatures across the same array. What we show here in the picture is just an example of a residential system where very commonly modules in the center get hot, modules towards the edge run cooler. In commercial and fixed tilt arrays, the same effect happens, and it's slightly different, mainly because when you're at a fixed tilt, the modules in the corner have more wind load. So you'll have the same patterns developing, but driven by slightly different thermodynamic effects. So we instrumented a number of sites and found an average of 4 to 7 degrees C as the range between the minimum and maximum. And we actually noted a maximum of 20 degrees C spread between the hot and cold modules. Given typical thermal coefficients, this is a 2 to 4% mismatch in power between modules. And again, this effect is not just seen in Tigo data sets. A representative of First Solar, speaking at a conference a few months ago, or actually, about a year ago, noted that they often see temperatures differing by 10 degrees C in their arrays in ground mount. So very commonly, mid to high single-digit differences in degree C on both commercial and residential systems, and of course ground mount with the first solar data. Now, in addition to the thermal mismatch, there's also degradation that grows over time. This is one of the key insights that we think many in the industry aren't properly accounting for. On the top right here, this is a histogram that was measured by NREL. Again, the detail on that paper is at the bottom of the slide here. They noted that there are a wide range in degradation speeds between modules. So yes, while the average module degrades at 0.7%, they're not all degrading at an even 0.7%. Some are not degrading at all, and that's shown by the histogram around that zero value. And then some are degrading much more than 0.7%, in fact, up to 3 and 4% per year degradation. So we were able to actually translate that histogram into what that contributes to the actual standard deviation across an array. So this exact histogram would be equal to a 0.75% increase in standard deviation, which is actually, if you compare that to the cloud base that we saw, that's an appropriate value to look against that 15% from the irradiance standard deviation that we saw. And that actually grows over time because these are annual numbers. So that's 0.75% per year. So in year 5, that'll be 3.5% standard deviation, just driven by the fact that modules are getting spread out. Now, on the chart on the bottom left, this is the power impact of that spread. So as you can see, the white curve is just driven by the mean shift, just by the average module going down by 0.7% per year. But on top of that, there is an increasing loss due to the variable component of that, due to the fact that they're actually getting more and more spread out over time. That equates to a few percent in year 5 and 4% or more in year 10. So it's an effect that's not very pronounced in the initial couple of years, but in years 5 through 20, it's absolutely a pretty major effect in the system performance. And this, by the way, is fully seen in many systems. There are a number of cases where people have looked at systems that are 5 years old and looking at a system annual loss of 1 to 1.25% per year. Again, that's the difference between a module degradation and a system degradation. Even if all the modules are within their warranty, the mismatch created by those modules will increase the system loss in the out years. So pulling all these factors together from the point of view of mismatch, we can actually model their impact on system energy and how much a product such as Tigo's maximizers could actually gain back. So on the low end, if we just assumed 4% irradiance mismatch, again, that's compared to the 10 and 15% that we saw in real-world data. If we assume just 3 degrees difference compared to the 4 to 7 that we found in our own, and if we assumed 2% module binning range, such as folks who will rebin their modules, then you're looking at a year 1 mismatch loss of approximately 1.5%. On the other hand, from the high point of view, if there's 10% irradiance mismatch, 7 degrees C difference between hot and cold modules, and a full 5% module binning range, then that would correspond to about a 7% mismatch loss in year 1 before accounting for the variability that grows over time due to that degradation. So again, there's a growing science around how to properly characterize, understand, and quantify the amount of mismatch that's in a completely unshaded array. Now, when it comes to expanding a system size, there are a number of ways that we can actually help to expand the size of a system. Now, I want to point out here, this is a very different factor than what I was just talking about with the energy yield. Everything with the energy yield says that for a given amount of nameplate power, we can help you squeeze more energy out of the array by reducing the impact of loss factors on that system. What we're talking about here is taking a commercial rooftop, and because we can bring shade tolerance, because the maximizers will prevent the shaded modules from bringing down the strong modules, then we can help a developer expand the amount of addressable roof that they can build a system onto. Now, especially in commercial arrays, because you often have a lot of space, and there are often lots of obstructions on that rooftop. What we can do is actually import the direct Google SketchUp file or the 3D CAD file from the developer and put that through the modeling software that we mentioned earlier. So with that modeling software, which is by a company called Folsom Labs, we can actually look at the energy yield of all the modules and expand the size of a system. We've seen anywhere from 5% larger systems to 2x larger systems, as you can see here, where we took a system from about 1 megawatt to about 2 megawatts. And the reason we can do that is because, again, in the areas that traditionally are extremely shade intolerant, you just basically have to take a design rule that you're not going to put modules into marginal areas. With maximizers and with our software's ability to give a very rigorous estimate of what the energy yield will be, now developers can be very smart about where they expand the size of their system when they're using smart modules. And as we're doing that, we can actually show those developers the exact energy yield that comes out of each module. So these small numbers here are actually the annual kilowatt hours per module per year. So this helps a developer be much more intelligent about what the actual energy yield and financial payback will be on a module-by-module basis. So again, when you're talking about designing the right size system and expanding the system, this data is critical. And we can show this both with and without smart modules so that they can both understand what their best case scenario would have been without Tigo, but then also how much better off they are with Tigo. Now, when you've got that type of module level data, you can also show module by module how much better off the system is with and without Tigo. So in this scatter plot, for example, this is again for that initial rooftop that we saw earlier. We can look at all of the all of the modules in the array, and on the x-axis that shows the energy yield in watt hours per module per year. On the y-axis is the energy yield of each of those same modules when we can apply Tigo to the system. So this really helps the developer understand where we can help, again, not just at the aggregate level, but which modules we can help out with. And just to show one example here, this is a case where you can see the modules in the solid circle towards the center. Those are modules that are pretty significantly shaded. And of course, when you put a smart module on an array, we can't solve the shade problems by eliminating the shade. If there's shade, there's shade. We can't bring back the sun. However, what we can do is we can prevent those shaded modules from dragging down their peers. And as you see the dashed circle at the top, those are modules that otherwise would have gotten significant sun, but without Tigo, their performance would have been severely hurt. You can see that for that dashed circle, those modules would have, without Tigo, delivered only about 200 kilowatt hours per year, and with Tigo, they're over 350 kilowatt hours per year. So basically, these tools plus Tigo can really help a developer understand, where Tigo can help their system. So these become a really hard number ROI-based decisions about, where to intelligently apply smart modules. Now, in terms of expanding system size, it's not just a matter of shade tolerance and expanding into shaded arrays. We can also help with ground coverage ratio. So this here is a somewhat famous chart from, it's both available in PV watts as well as, you can see the sources from Powerlight. So the basic intuition here is pretty simple. As you increase ground coverage ratio, the shading losses start to grow because you start to have cross-bank shade. Now, when you apply Tigo to that, we can actually model those same systems with and without Tigo. Now, of course, without Tigo, the curve looks very much like it does before. When you apply Tigo, we can help with those cross-bank shading losses. Now, the effect grows the closer you get, which also makes sense. And note that at a 70-degree ground coverage ratio, we can improve the D rate from 75% to 82%. So we can gain a full 7% in energy yield when you've got that type of ground coverage ratio. But of course, most people don't design systems that are that tightly packed. And at a smaller level of ground coverage ratio, our effect is on the order of 3 to 5%. But still, that means that when you have module-level optimization from a smart module by Tigo Energy, you can increase your ground coverage ratio by roughly 5% and still have the same system energy yield, which means that you can have a 5% higher nameplate power, and all of that increases the actual profits on the array. Now, just to illustrate how important the system expansion is, we've shown here both some real data that we've got from customers on the left side, where we can actually work through the financial model with a customer and help them understand how much more profit this system expansion gives them. But additionally, I've got just almost a qualitative example here. So when you've got system economics. It's driven by both the marginal costs, such as modules and racking and inverters, and fixed costs, such as the overhead, and actually in some cases a lot of the on-site hardware, such as in racking infrastructure, et cetera. And then, of course, the profit margin. Now, when you can expand a system by 5%, not only does your profit grow by 5%, but your fixed costs don't grow by 5%. So in practice, the overall system profit grows in proportion to both the profit and the fixed costs, which means that as module prices come down, the module costs, which really drive the marginal costs here, are getting smaller and smaller, and therefore the benefit of expanding a system is growing more and more each day. And just to show an example here, if you take 75, 15, and 10% cost breakdown, which is, again, a very rough number, at $4 a watt, that's about a 5 cent per watt total impact. So, just having a 5% larger system gives you on the order of 5 cents per watt larger system. And as I said before, we can often get 5 to 15% greater system size, and sometimes it can be as much as 100% greater system size. So the profit potential of this is very, very large. I'm showing here essentially one of the most conservative cases. Now, in addition to having a higher nameplate power for a given rooftop, we can also help to reduce the electrical costs on a system. MJ made some reference to this earlier. So just to show what we're talking about when we talk about stretching strings by 30%, traditionally a module has an IV curve that looks like this. And of course, at open circuit, the module voltage can be as high as the VOC, the open circuit voltage, and designers have to rate to open circuit at the coldest temperature. Now, when you've got a smart module, we can actually prevent the voltage from going above VMP at STC. And that's the case for any voltage level, for any temperature, and for any load level. So what that means now is that instead of designing to VOC at the coldest temperature, which sometimes might be on the order of 50 volts, now you can rate the system to the VMP of each module, which might be around 35 volts. So that makes the strings longer because now you can put more modules on the same home run conductor. The first benefit of that is that with more modules on a string, you now have an array that has fewer home runs, which means less wire, fewer combiner boxes, and less direct labor that's needed to install all of those components. Roughly, it tends to be a 25 to 35% benefit, and that, of course, depends on the exact module that you're using, the exact inverter that you're using, et cetera. But in general, your full electrical BOS will be reduced by roughly 30%. Additionally, the IR losses on those home runs is also decreased because while the number of conductors goes down by 30%, the actual nominal current on those conductors isn't any different. It's actually the voltage that goes up, and largely voltage is free. So because we can reduce the conductor count by 30%, that means that the IR losses are actually going to go down by 30% as well. So fewer strings is a huge benefit, not to mention the design benefits that gives for designers who oftentimes are constrained by whatever the inverter's min voltage is and max voltage is. Additionally, having longer strings is good for inverters. This gives a couple of benefits. On the one hand, we can help to remove the boost stage of an inverter, particularly for inverters that are constrained by 600 volts on the DC side and 240 volts on the AC side. Generally, they need boost transformers to keep the voltage within its operating range. With these longer strings, they no longer need that boost stage. Additionally, with longer strings, that means that the average voltage is actually higher and the minimum voltage is higher. Now, on the right here, I've got a spec sheet for an off-the-shelf SMA inverter. And as you can see, this inverter ranges from 500 kilowatts to 800 kilowatts. The difference there is not the actual hardware necessarily. It's predominantly driven by the higher voltage range. When it can increase the voltage in from roughly 300 plus volts to in the mid 400 volts as the minimum voltage in, that inverter can be rated at a higher power level. And this is exactly what MJ was talking about early on. By having a higher and tighter voltage range, inverters can, for the same amount of hardware, have a higher nameplate power, which of course helps to reduce cost in the industry. So these are all benefits in the upfront. Now in terms of the system over its lifetime, there are also a number of field operations benefits that you get when you've got module level electronics. So one of the first ones is the fact that with module level data, diagnostics can be much faster. This is a chart from a study that we worked on with Altaterra Research, and they found by speaking with a number of developers, many of which who had experience with module-level electronics, that there would be a 1 to 5% reduction in the ongoing O&M costs when developers can have access to that module-level data. And the basic logic is pretty straightforward. When you've got module-level data, you know exactly where problems are, and you know exactly when they happened. So truck rolls can be done exactly when there are enough problems to merit that labor, and they know right in the field where to go troubleshoot and fix those issues. Additionally, they mention on the first line here that there's an expedited commissioning process. That's actually something that is also extremely real today. So one of the nice benefits of the maximizer system is that on commercial systems where there's a third-party engineer and typically a bank ownership of the project, we've actually been able to generally have the independent engineers not require IV curve tracing. And the reason is that when you've got module-level data, we can generate a commissioning report that's based on the maximizer data that actually can give them all the same information that they're looking for with that IV curve information, but with actually better quality. So they can understand the health of the system, the balance of the system, and the general performance of the system. So basically, you know, this is a great benefit to the independent engineers because they actually get more information. And on the projects that we've done this with, they've all acknowledged that they actually prefer this to IV curve traces. And obviously for the developer, not having to spend all that labor running IV curve traces on a commissioned system is a very nice labor benefit that they get right up front. As you can see here, we can actually send out examples of this report for those who are interested in learning more about this. So right off the bat, we can help with the labor content of what it takes to get a system together. Additionally, of course, you've got field analytics. Now, I would argue that there's sort of a beginner's and advanced level of this. The beginner's level is, how are my modules doing? And that's kind of what you can see here. When you've got module-level data, you can look across an entire field. You can easily spot any modules that are weak versus their competitors. However, we need to take it a bit beyond that, because while it's one thing to know that you've got a problem, it doesn't necessarily tell you whether you've got a dirty module or a problem. This on the right actually is an arc fault where there was a high resistance solder connection between some of the cells. And so one of the important things about maximizer data, because of the quality of our data, we're collecting data every 2 seconds, accuracy much better than 1%, and it's all completely synchronous. This means that we alone have the ability to understand what's going on at each module. So we can actually show the story of what happened to this module when this fault happened. So this is from an array in Northern California. It was a commercial array. And these are 240-watt modules that, for a brief moment, are producing nearly 300 watts. So these modules are running at essentially 125% of their rated power. That's because, as you can see from the shape of the chart, it was a cloudy morning, and then as those clouds moved off at roughly 11:30, they reflect some of the sunlight back onto the initial modules. So that's where you get greater than one full sun worth of irradiance onto a module. So that's a lot of current, and in this case, there was too much for that weak solder connection. And you can see, based on the blue curve here, that it was essentially dropping out a bit. And then it was the arc actually sort of extinguished itself just past noon as it essentially caught up with the other modules in the array. But then even later in the day, you can see it starting to arc again. Now, that failure continued through the next day. This is just sort of a regular sunny day, again with clouds in the morning. And on this day, that module was about 15% weak versus its peers. But on the very next day, we had a case of a very cloudy day. And this can be shown here. You can see it with the 2-second data. And again, these are the kind of high-altitude clouds that we saw with that Hawaii data that I was showing earlier. Now, this not only causes mismatch across the array, but on a failed module like the one in this case, it's wreaking havoc on that connection, mainly because you've got very low current, very high current, very low current, very high current, and that just keeps hitting that weak spot in the connection. And because of that, you can see that on this day it's much lower than its peers. And then finally on the last day, you can see that again on a sunny day, where at least by about 11 o'clock and through the afternoon, there's good even sun, you can see that this weak module here is, by that blue curve at the bottom, not only extremely weak, now it's about 60% weaker than its peers, but it's got a very high voltage oscillation, which is a characteristic pattern of an arc. So now the key thing here is that we can use this data, and we're picking up a number of these things throughout our system, to help design algorithms based on our own maximizer data that can help us spot these in the future. Here's a different example. This is a module that was damaged during shipment. So you can see that the front glass was essentially shattered, and because of the glass type, the whole module front was shattered like this. And again, this is the pattern of voltage oscillation here on the right-hand side. Now, what's interesting, if you compare those two fault types that we just saw, the high resistance arc and the module shattering, you can see that the pattern of the way their voltage oscillates is quite different from each other, both the magnitudes and the way that the speed changes throughout the day. This is part of how our analytics on the back end are helping us understand what each fault type has as far as its unique signature. So in addition to the ones that I've showed you, we've got a number of cases of cracked cells, of oxidized cells, such as the one here in the top center. Hotspot connections, that's on the top right, where you can see where the copper looks a little bit green almost. And so each of these actually has a unique pattern in the data. And that's where, with the maximizer system, smart modules in the future will have a very high advanced level of diagnostics. So it's not just a matter of saying you have a module that's 15% weak. It's a matter of understanding whether the right corrective action is to clean it off, or replace the module, or just replace a diode if you've got a failed diode. So that's the future level of operations and maintenance that's enabled when you have smart modules with electronics behind them. So just pulling together then the overall set of economics that we've got here, as MJ said, the cost of electronics is anywhere from about 10 to 20 cents per watt, and often that can be paid off right in the first year. As we mentioned with the electrical balance of system cost reduction by reducing strings or by extending strings by 30% and reducing the electrical BOS cost, that gives us approximately an 8 to 9 cent per watt cost advantage. With higher powered inverters, that's a few cents per watt. And with the system expansion, again, often between 5 and 15%, that would be anywhere from 5 to 15 cents per watt of incremental profit just by having a larger system. Then over time, we can bring benefits of energy harvest, of O&M savings from both having smarter truck rolls and from reducing that commissioning labor, and finally from having better system uptime because, again, as you spot those problems, first of all, we can localize the problems so that they're not causing the rest of the array to go down, and of course we can help them get fixed faster. So you no longer have problems waiting months and years to have somebody spot them. You can spot them right away and fix them as soon as it makes sense. So again, basically, we're at a point today very similar to what MJ showed early on, where module-level electronics can largely pay for themselves upon installation. And then all the future benefit is just additional financial benefit to the system owners, both in terms of having the energy harvest and in terms of having that type of data. Now, with just an hour, it's sort of tough to go in proper detail with all these benefits that we've got here. So as far as next steps go, I encourage anyone who found this interesting to follow up with us. And there are a number of ways that we can engage. First of all, we have the ability to do this performance modeling that I mentioned earlier. If you just send us your CAD and or SketchUp files to sales@tigoenergy.com, we can run that system and show your system with and without Tigo, both in terms of either just mitigating shade and showing what the delta is if you have a shade obstruction, or if you had left portions of the array undeveloped due to concerns about shading, we can help you understand how much more of that shaded area makes sense to add back in when you've got the benefit of module level optimization. Additionally, we have a pretty robust LCOE model. A lot of the financials that I showed throughout here are very specific to the application, depending on the module type, depending on the location in the world, depending on the type of system design approach that you've got. It will have an impact on the actual payback period of the maximizer system. So we'd be happy to take anyone through that And based on each customer's unique set of cost structure, we can help them understand what the benefits are of Tigo and where that payback will come from. And then finally, as I mentioned, there were a number of pages here where we had this icon, the green bar at the bottom. If any of that was interesting, please email us at sales@tigoenergy.com, and we can send either the data packages and or some of those example reports from things that we've done. And so with that, I think we've got time to open it up for questions.
Great, Paul. Thanks for that very comprehensive presentation. As Paul mentioned, we do have time for questions. We've had a few roll in during the presentation, but if anyone has any questions on what Paul has presented, or maybe some questions about that you have about Tigo or module level power optimization that he hasn't covered, please feel free to type into that box. So let's just get started. First of all, let's just do a quick, I think, housekeeping question. You had early on in your presentation, and I'll push the slide, this early slide about the energy impact of some of the factors you talked initially. And we have some questions about how is this year one mismatch loss calculated? Is this modeling, or is this a general rule of thumb that you're using?
Yeah, great question. So this is modeling. And as I had mentioned early on, we have the use of a new tool. Traditional tools such as PVSYST or PVSOL or PVWatts treat these factors as just global loss factors, and they just apply a global haircut to the whole array. What we've got now, and it's you can see in the footnote here, something called Folsom Labs is the company that's developed it. It's a full performance model based on module level production. So basically, rather than treating an entire array like it's a single diode, which is what PVSYST does, this model has the ability to design out each module in the array, and then for a full 8760, so running a full year every hour of the year, calculating the actual energy production out of each module. That's specifically based on what the irradiance is of each module, what its operating temperature is, how it's wired in series. It then, if you have a string of 12, it puts those 12 modules in series. All of the standard system engineering, obviously modules in series have the voltages at and they're current constrained, and then those are all sent to the inverter with the inverter's MPPT algorithm choosing the peak operating point. So with that type of rigor and having that sort of intense mathematical calculation, because that's basically a lot of math behind that, that gives us the ability to then apply these types of mismatch factors and understand what that does to system production. So basically what you're looking at here is the actual modeled result out of this software that allows us to basically apply, for the irradiance, it applies a normal distribution. For the temperature difference, it applies a linear distribution. And for the module binning, it of course applies a linear distribution, because that's by definition how they are. If you buy a -0 + 5% module, you expect an exactly linear distribution between that module's nameplate and nameplate plus 5%. And so essentially it applies these factors to each of the modules, and then again it's running a full 8760. Now one of the interesting things here, and again because this is a webinar, we just had to pick a typical number and then show this for typical numbers, but I would say in general these numbers vary a lot based on the exact system that you're looking at. So whether you've got a string of 8, 10, 12, or 14 modules, whether you have a module with a high fill factor or a low fill factor. High fill factor modules are generally not very mismatch tolerant, because if you think about what a high fill factor means, and for those who are less familiar, high fill factor is essentially sort of synonymous with high efficiency. The higher your module efficiency goes, the IV curve has a very sharp knee. I don't have any IV curves here in the presentation, but I think most people are familiar with them. They're typically on a data sheet. As the fill factor gets larger, that knee gets sharper. And when that knee is sharp, when it's a very steep curve, that means that as soon as your current starts to be mismatched, you start to lose a lot of energy. So my point is simply that here we just took a pretty pretty common 280-watt module. But depending on the exact module technology that you've got and the exact string length and the exact inverter type, these numbers can and will differ. So these aren't meant to be be-all, end-all, but they are meant to be illustrative. We basically picked sort of mid-range string length, mid-range module design, a very common inverter type. But again, there's really no substitute for going through the full math.
Right, and just to make sure everyone is on the same page, you talked about binning, and it's on this slide as well. Can you just go in 2 seconds what you mean by module binning? Sure,
absolutely. So when someone buys a module from a module manufacturer, let's say you buy a module that's a 280-watt module. Not all those modules are not exactly 280 watts. The manufacturing process has natural variance in it. And so what manufacturers do is they bin up those modules. So they might have a bunch that are 280.1, 280.3, 280.4, et cetera, all through the range. And so when you buy a product that's nominally a 280-watt module, there's often a tolerance around that value. Now, those numbers typically are plus minus 3%, plus minus 5%. More recently, the range has both gotten smaller and moved up. So often there's positive tolerance modules. So if you buy a 280, you're guaranteed that they're all going to be minimum 280 at sort of standard conditions, but perhaps as high as 5% higher than that nameplate power. And so the importance of that, again, from the point of view of Tigo, is when you buy that bin, and let's just say for the sake of discussion that it's 280 watts plus 5%, then a number of those modules are actually 5% better than 280 watts. Well, when you've got maximizers on that array, we can make sure that those stronger modules are able to produce their additional power. Versus if you didn't have maximizers, then again, each of the strings would be constrained by the weakest module on the string. And so that range that's really a natural part of the manufacturing process does create some mismatch between modules. And one other point there, some folks will actually re-bin their modules. So if they get modules that are 280 plus 5%, so it's a full range from 280 to, what would they be, about 295, then they may re-bin them to subsections that have an even tighter distribution and make sure that those are on similar strings. With Tigo, that practice isn't necessary because, again, instead of applying human labor to sorting each of the modules that developers are using on a commercial array, now you can use smart modules to instead manage that mismatch and make sure that the strong and weak modules are always running at their optimal power. Great, and we have a few just one housekeeping note. This webinar will be available for replay at greentechmedia.com, and you can also download the slides in your interface in the lower left-hand corner. Moving on to the next question, we had a few questions about increasing the nameplate rating of the inverters. And first of all, how does this interplay with the certification, or the warranty, or even just the reliability and the lifetime of the inverter itself? Good question. So in terms of certification, many of these are off-the-shelf inverters. So there are some manufacturers that are developing specific inverters paired to this technology. I'm not at liberty to mention who those are. But again, what I'm showing here is truly an off-the-shelf SMA. I got this right from their website about a week and a half ago. So many of these exist in the market already. Now, the only difference is in the certification of the smart module. And I'll just speak to that very briefly. The basic way this is done is when you've got a smart module, and actually I'm going to go to a couple slides ahead here, a couple slides back. When these smart modules are listed, instead of listing the open circuit voltage and a temperature coefficient, the module will still have a temperature coefficient because for temperatures hotter than STC, the voltage can be below VMP. But as I said, we can control the voltage at VMP, and that'll stay there even at colder temperatures where the voltage on the silicon would typically be higher. We're still going to be able to control that from the smart module that's located right behind that module. So the module itself will actually be rated with a separate value. We call it the V limit, which also is equal to the voltage at open circuit. So if you notice here, we show VMP/VOC. It's not the same way you think about VOC traditionally because, again, essentially the system will never see the open circuit voltage of the silicon. But strictly speaking, when that module is at open circuit, the maximum voltage will be exactly the VMP. So basically with these smart modules with smart curve, the VMP and VOC are equivalent. So it's a bit of a neat little trick of sort of how you can define how a product will behave. But this is a pretty normal part from a compliance point of view because if you think about it from how a CSA TUV would look at that, it's nothing but a voltage regulated device. And while this is a unique situation from the point of view of the solar industry, those places are quite comfortable with voltage regulated devices in other industries. So they're very comfortable with how to test and certify those products. And then from the system point of view, there are a number of code changes that give specific authorities having jurisdiction, the AHJs, direction to follow the guidance of the manufacturer in terms of how these products are to be designed. So again, it's a matter of simply having all the proper documentation, which is quite a solvable problem, and then you can basically again design your strings to the exact VMP with no temperature derate, and get it through both the component level certification through CSA TUV and UL, as well as through local AHJs.
Sure, and so that certainly is, that certainly does change the behavior a bit. But what happens if, and of course this would never happen in field, but let's say that one of the optimizers fail. What happens if you've already planned that into your longer strings and are raising the nameplate rating of the inverter? How does that affect the system?
Yeah, good question. So the way the mechanism works, it's predominantly a software mechanism. So it's done through the algorithm that's part of a smart module, but there's also a hardware backstop. So there are specific components inside the smart modules that enable smart curve that will prevent the voltage from ever going above that value of V limit under any circumstances. So even in the case of a failure, there basically would never be voltage greater than the rated voltage of that module.
Sure.
And that, by the way, is part of the certification process with the component level certification for that voltage limit. It will basically be rated to produce that maximum voltage under both the range of temperatures and loads, as well as under the full range of fault types. And so that's going to be part of the inputs to the certification.
Okay, great. So moving on, and you have all these data packs available. You have all this data from the installations that you have. So moving away from the optimizer itself, can you, based on Tigo Energy's experience, what tends to be the problems that occur in terms of reliability of the module? What are the common failure points? You have all these diagnostic tools available to you now. What are you seeing as the main points of failure in these modules that have been installed out in the field?
So I think the first point I would make is that good modules from good manufacturers are extremely reliable. Now, Tigo is never in the business of naming names and saying who's good, who's bad, but I would say that our partners for smart modules are extremely good, and we see extremely low numbers of issues from really any of their modules. Now, that being said, to answer your question, what are the most common failures? Just in terms of raw numbers, the most common failure is actually quite simple. It's just a failed bypass diode. Modules typically have 3 bypass diodes. When they're installed, if one of those diodes is bad, then that module will be producing voltage that's 1/3 approximately lower than the other modules in the system. We have, since the very beginning, seen approximately 0.3 to 0.5% of modules that have a failed bypass diode upon installation. There are a number of case studies where, on a commercial scale array, we'll find 10, 12, 15 modules with failed bypass diodes and just send them back right away. And it's actually a really nice point in time to find them. And one of the points that we often make there is, let's say you've got a string of 13. So a failed bypass diode is going to be approximately 1/3 of one module, so that's about 2.5% of that string's voltage. Very difficult for even a trained technician doing the IV curve tracing the proper way to be able to spot that, because just the measurement error is often swamps that 2.5% delta. So bypass diodes not only are sort of the most common of generally a low set of numbers, because again I want to repeat, modules are nice and reliable, but when they do happen, they're extremely hard to find, even when you're commissioning the system just the way it should be done by the book.
Great. So I think we have time for one more. Again, we've gotten a lot of questions, a lot of product-specific questions as well, which I'll leave to Paul and his team to answer following the webinar. But I guess no presentation on module level optimization, especially just talking about DC optimization, would be complete without me asking, so you have all these features that are available for DC optimizers, but some of these can be done by microinverters as well. So what's the difference here? Why should someone choose DC optimization versus using a microinverter?
Yeah, great question. And actually, I'm going to switch over to the slide where I summed up all the benefits, because you can sort of just, even based on intuition, look across the numbers here. So in general, microinverters are going to give some of the benefits of what module level smart modules give. So for example, the system expansion would generally apply to them, the energy harvest, and the O&M savings. Now the other ones would not. The electrical BOS, actually the cost of the conductors on a microinverter system are pretty high, and I believe the BOS costs from the cost comparisons that I've seen tend to be higher. Of course, higher power inverter doesn't, they're actually going in the opposite direction. And then I suppose some of the system uptime stuff would apply as well. So they don't get all the benefits that we're talking about here. But if I take a step back, so rather than just looking one by one and trying to answer it sort of by looking at each line item, there is a pretty big difference in terms of the maximizer cost compared to a microinverter. So I think in general, microinverter costs are roughly 65 cents per watt. And then again, as you had shown in your slide, our costs tend to be between, let's say, 10 and 20 cents per watt. Now that number depends very much on the size of the system. Our system scales extremely well, so as you get to commercial and ground mount multi-megawatt scale systems, the cost per watt can decrease even on the gross cost level down towards 10 cents per watt. And then, of course, when we can offset that elsewhere in the system, the net cost gets into the low single-digit pennies per watt. Microinverters don't get that same scale benefit, because when you do a large system with microinverters, or if in theory you were to do a large system with microinverters, you would just be replicating that 65 cent per watt microinverter on the whole system. So in general, the biggest difference is the size of the system. When you're looking at a roughly 3 kilowatt or smaller system, microinverters can be quite cost competitive, even when compared with a central inverter plus a DC optimizer. That break-even point is roughly around 3 to 4 kilowatts. And then as you increase the system size, both the price per watt of the inverter goes down, as well as the price per watt of the maximizer, or you might call it the smart module premium if you're buying the module, the smart module from some of our smart module partners. And so that combined cost on, let's say, a commercial scale system you might have a central inverter at 25 cents per watt, and let's call our price premium 13 cents per watt. So now you've got a 38 cent per watt fully loaded cost for that system compared to, again, 65 cents for microinverters. So basically, the 65 cents looks good when you've got a 2.5 kilowatt system. When you've got a 500 kilowatt or a 2 megawatt system, that 65 cents per watt is not very competitive. But other than that, a lot of the high-level stuff does apply. Of course, they deliver module-level optimization. They deliver module-level data. The one thing I would say is that the section here, I'm going to jump to this slide here. Most other products on the market, as far as I know, all other products on the market, only provide data roughly every 1 to 5 minutes. And that's because they're not polling every 2 seconds because they're not doing the same type of system approach that we are. And so the quality of the data, if you measure quality by, first of all, synchronicity, second of all, frequency, and third of all, accuracy, is going to be much, much higher with smart modules enabled by Tigo Energy. So that is a point where head-to-head, we're going to do much, much better. And then, of course, just keep in mind that from a system efficiency point of view, maximizers are 99.6% efficient. So that plus a good central inverter compares very, very favorably to a microinverter. So again, we always encourage people to frame it as a question of cost, efficiency, and reliability / part count. And on all of those measures, if someone does their homework, they will find that a DC optimizer plus a central inverter is going to stack up better than a microinverter.
Great. Yeah, and certainly I think our underlying thesis is the same at GTM Research, though. I mean, certainly with larger systems, you would use you wouldn't use a per module microinverter necessarily. And of course, when you think about DC optimizers, I think you did reference this, but it's always good to keep in mind that you do have to pair it with the inverter cost as well. But anyway, we are basically a few minutes over, but I just wanted to thank the audience members for their time. But before we end this webinar, Paul, are there any last words that you'd like to give?
Not really. Just, again, as MJ mentioned, with all the questions, we'll do our best to follow up with everyone directly. And just want to, again, show the slide we've got here. If anyone is interested in taking a look and essentially sort of kicking the tires on what our impact is on a commercial scale system from a production point of view, getting a better understanding of how the financials stack up when you take an all-encompassing view like I've shown here, or if you want some of these data packs, please email us either sales@Tigo Energy or paul.grana@tigoenergy.com.
Great, and I'd like to thank everyone who attended and who asked some great questions, and thank you again for making this another great webinar from Green Tech Media.